Okay, this one is kind of interesting because it basically avoids some of the work we need to do. The work needed in this method is that when you look at this equation, you need to solve for A inverse, right? Or you need to somehow get the solve for A zeros by taking that and making diagonal elements go to 1 by the Jacobian method, right? So that's a lot of work, and we want to avoid that. In this method, I'm going to tell you actually avoids that. It's a smart way of writing the polynomial equation so that you don't really have to deal with this whole mess of inverting the matrix. So the second method is called Lagrange interpolation. Okay, so this method, like the polynomial fit, uses nth order polynomial, but uses a smarter way of writing the polynomial that avoids the computation of the inverse. Okay, so I think the best way to illustrate this is to actually solve the problem. So we just take the same example and we'll solve it using this method. So it's essentially the same problem. Using interpolation. Okay, so first of all, we note that we do need a second order polynomial because there are 3 data points. So what Lagrange interpolation does is it writes a second order equation in this fashion. It says it's A0. You know what? Let me use a different index not to confuse you with the A's. So what we'll do is we'll take, so 0, 1, and 2. Okay, so we'll take all combinations of 0, 1, 2 in pairs of 2. What I mean by that is, so we have x minus 0, x minus 1, x minus 2. So we took 1 and 2. So so remember, we need all combinations of all combinations expressed as a polynomial of the values of x up to order n. So 1 and 2 will give me x minus 1 times x minus 2 plus b1. Now we'll take everything but 1, so x minus 0, x minus 2, and then finally b2, x minus, so what's left? 1, 2, 0, 2, so x0, x minus 1. Okay, everything here is a quadratic equation. Like we need a quadratic equation for sure. So everything here is a quadratic equation. And now I claim that because of this assumed form, it's super easy to find b0, b1, and b2. Okay, let's try it out. So let's just move this. And I'll put this table. Okay, so that's just for reference. Okay, so let's start substituting. Okay, let's put y equals, so x equals 0, y equals 2. This is basically the first column, 0 and 2. Okay, so what will happen if you do that? Well, you have 2 equals, so x equals 0. So what you notice here is very interesting is that when you put x equals 0 in this equation, 0 minus 0 is 0. So everything there will be 0. If you put 0 here, 0 minus 0 is 0. So everything times 0 is going to be 0. So you'll only be left with the first one. So b0, 0 minus 1, 0 minus 2, plus 0, 0. So b0 is simply, it's 1, I think. Right? Okay, next we put x equals 1, y equals 0. So we have 0 equals, again, when you put 1, you will notice that this term, if you put 1 here, it will be 0. If you put 1 here, it will be 0. So the only term which will contribute is this one. So b1, 1 minus 0, 1 minus 2. But anything, well, this will only give me b1 equals 0. Okay, and finally, if we put x equals 2, value of y is 4. So 4 equals, when you put 2, the first term will be 0, the second term will be 0, the only third term remains. So b2, 2 minus 0, 2 minus 1, b2 will be 2. We are all set to substitute. So y equals, I'm going to substitute back in this formula. 1 times x minus 1, x minus 2, plus everything here will be 0, plus, because b1 is 0, and the 2 times x minus 0, x minus 1. So this will be x squared minus 3x plus 2 plus 0, doesn't matter. And then you have 2x squared minus 2x. Okay, so when you do the addition, you have 3x squared minus 5x plus 2. Okay, so here's the equation. 3x squared minus 5x plus 2. And if we compare that against what we got using polynomial here, well, it's written the opposite way, but it's 3x squared plus minus 5x plus 2. Is it what we got? 3x squared minus 5x plus 2, 3x squared minus 5x plus 2. We got the same answer, but we didn't have to invert any matrix.